Mugume gyali ne banna.
I almost died. Huh? I almost died. I don't know. I don't know what happened. Things are hard, man. Sure. Me, I know my problem. Since primary, I'll just sit and watch.
You see the schedule? Man, I was
Morning, sir.
Hello, good morning. Welcome to this lecture. I hope you had a nice weekend and good rest. I think I'll start with a few announcements. I talked to Jesse, who is one of the class representatives, and he said that you guys sort of agreed to do the exam or the test on Saturday. Saturday is what? 18th. So yeah, Saturday 18th. So I'm happy to do that. I don't usually put things on weekends because I want to be considerate to you. But if you want to do it on Saturday, that's okay. So we can do that on Saturday. If there are any people who have a different view, this came from your class representative. So I imagine that he would have consulted widely.
Excuse me, sir.
Yes.
On the same subject matter.
Yes.
We sort of didn't agree because just actually brought up a suggestion up today.
Yeah.
And we had the same discussion, and we're telling him it would be better to arrange for the test next week because for all of this week we are really pretty packed. But we're kind of wondering how the conclusion has gone.
Emma.
Yes, sir.
What year are you?
Year one, sir.
So why are you packed? I don't get it.
We are having a test today. We are having a test on Wednesday. We're having assignments. We're having a test on Thursday. Also, there is another one which they had suggested on Friday online.
So basically, it is mine that you feel should be pushed.
We're requesting if it would be possible on Monday.
This is really a conversation I don't want to get involved in because I can just say, let's do this test in my class time and we will do it. But I thought that you people need to, first of all, agree and come with one position. I've already moved it to Saturday. Now you're telling me Monday. I don't know what to do because I'm just talking to you. There are 200 other students with different opinions. So guys, go and agree. But I would really prefer that the test is done this week. And I don't know why it is mine that has to be pushed, but that's okay. I still don't have an issue. So let's close that, and I'll expect, proper feedback at least before the end of the day. But the excuse of you being packed is really not an excuse. I understand I was a student, but I think that's really not an excuse because this is the time we have, and I'm not trying to put my test in a time that clashes with another test. Okay, so so that much I don't agree with. I think really that you just have to be a bit positive and be, if you have to study the whole night, so be it. I'm sure you did it in high school anyway. The course is not simple. All right. Yeah. So if the class representatives, okay, I'm going to talk to the class representatives myself, but I think as of now, we are going to do that exam on Saturday. I didn't hear anything on Saturday. I had something on Friday, so you'll have a day to read. And I told you at the beginning of this course that whenever I teach a class, you need to actually go through that material. If you wait for things to pile up, you're going to be in real trouble. So last week we talked about flip-flop applications. And I would, by the way, another thing is I sort of need all my lecture hours, but it's okay. If we have to do a test, we can do a test. And we did this, we looked at, this is a shift register. So this is actually a couple of shift registers. We are shifting information from one register X to another register Y. And all you need is to connect a flip-flop after the other. And then between the two registers, you connect the output of one register to the input of the next register. By the way, when you look at these registers, this will be hidden from you. So if this is a 3-bit register, this will be hidden from you. All you are seeing is that and the clock input and then this output. All right. So it's not like you have, unless you put this on some type of board. But usually if you go to buy a 3-bit shift register, you will buy a black box. Excuse me. So we looked also at the parallel versus serial transfer. And today we want to look at frequency division and counting. So we can also use flip-flops. We can arrange them in a certain way that we can divide the frequency, but also we can do counting. So counting is, I want to count 10 objects. How many bits do I use? I use 4 bits, because if I use 3 bits, they can only count a unique number of 8 bits, and so on and so forth. That's what we want to do today. But before we start, I want to redraw this diagram so that it is a little bit less complicated. So if I draw, okay, my pen is giving me some trouble. If I draw this flip-flop, I can put I want to see. I can put Q2 here, okay? And then I put my J and K here, and I put my clock here, and it is negative going transition. And I draw the next flip-flop. I put Q1 here, J, K, and the negative clock. And then I draw another flip-flop, which I can call, this is Q0, J, K, with a clock there. Then I connect these two. These are always connected to 1, 1. So that's a 1, that's a 1, that is a 1, and that is a 1. So they are always 1. And we know that when we have a JK flip-flops in which inputs are always 1, that is the toggle step. So every time you get an active clock transition, the clock, the flip-flop will toggle from one state to the other. So we have a clock here, which we know is an NGT. Now, if you look at this diagram up here, Q0 actually goes into the clock of Q1. So in other words, Q0 comes and runs the clock of Q1. And then Q1 actually comes and acts as the clock of Q2. So you have Q1 running Q2. Now, why have Mukalazi, please keep keep yourself muted. Why I've redrawn this one is because you see these large, connections would probably confuse some people. But when you redraw it like this, it really doesn't change anything. But at least it is much easier to now try to look at and understand. Okay, so you have a clock on the least significant bit, and then the output of that flip-flop runs the next flip-flop, the clock, and the output of that flip-flop actually becomes the clock signal of the third flip-flop. And I can add more flip-flops on this side, and the action will continue. So if we want to do frequency division, if we want to do counting, we connect flip-flops in this manner. The clock, the actual clock signal runs the first flip-flop. Okay, so you have your clock here, and these subsequent flip-flops will be ran by the output signal of the previous flip-flop. But for all flip-flops, you want to keep your J and K inputs as 1, so that every time there is an active clock transition, you toggle. All right. So now we are going to do a truth table, and I want you to be very attentive here. Please follow me, because this can be a bit difficult for students to follow. We are going to draw a flip-flop. We will say clock pulses, okay? And when I say clock pulses, I mean this clock, okay? Clock pulses, and I can have here Q2, Q1, Q0. Okay, so we are going to assume that before there is anything, everything is 0, 0, 0. I think that is, yeah, we can assume that everything is 0, 0, 0. Actually, I see that, either way we can do it. Let's make this Q0 so that it is in line with the example that I have already prepared. This is Q2, okay? Okay, so I'm just going to rub this, and also that. So we have Q0, and Q2 here. Now, when the clock, is before we apply the clock, or we are starting at a state where Q0, Q1, Q2 are all cleared, okay? So when we first bring our first clock, our first clock transition, what happens is that this will toggle, but remember Q0 is 0. So this will actually toggle. If it was 0, Q0 will become 1, okay? But when the clock came in, Q0 was 0. So for this case, Q0 was 0, so this will remain 0, because when Q0 is 0, there is no transition. And also Q1 was 0, so it will remain a 0. Again, Q2 will be 0 because there is no transition. Remember, the transition happens, okay, so for this case, transition happens if Q1 is moving from 1 to 0. If Q1 moved from 1 to 0, you would have an active clock transition. If Q1 moves from 0 to 1, there is no active clock transition. The other thing is that here, there is going to be a transition at Q1 if Q0 moves from a high to a low, which is an NGT, all right? So for instance, in this case, we see that Q0 has moved from a low to a high, so that is not an active clock transition. I hope everyone can get that, and I can say it again. Of course, here the transition happens when the clock moves from a high to a low. But yeah, okay, yeah, but at least with a toggle, okay? So that is, when I say 1 here, I don't mean the transition in this manner, I mean this is the first active pulse. So an NGT. The second NGT, we can go to it. But because here on Q0, we are moving from a 0 to a 1, that is not an active clock transition. And so Q1 will remain 0, and subsequently Q2 will also remain 0. Let us look at the next clock transition. If we have a clock transition, a second clock transition, what happens is that Q0 will toggle again. Q0 will toggle again because obviously, yeah, 1, 1. Now, remember that this one, Q1, so because Q0 is moving from a 1 to a 0, Q1 is going to toggle because its inputs are actually 1, 1. So we expect to have a 1 there. So Q1 now will move into the state 1 because of this transition from a 1 to a 0. And Q2 is waiting for Q1 to move from a 1 to a 0, but here Q1 has moved from a 0 to a 1, so Q2 will remain 0. In 3, this one will toggle again. So when it toggles, it moves from 0 to 1. When it moves from 0 to 1, that is Q0, it has gone back from 0 to 1, that is not going to trigger Q1 to change because that is a PG, that would be a PGT, yet we are waiting for an NGT. So in that case, Q1 will remain in its current state. Q1 cannot change unless Q0 is changing from a 1 to a 0. And so if Q1 hasn't changed, then also Q2 will remain 0 because Q2 would have to change only if Q1 changes in this fashion. After the 4th clock pulse, Q0 will transition again, it will toggle. And when it toggles from 1 to a 0, this is an active clock transition, which is an NGT. And you can see that that will actually cause Q1 to also toggle. Q1 toggles, when it toggles, it is a 1. Sorry, I made a mistake. I should say, okay. Yes, so Q1 was a 1, but because Q0 has made a transition from 1 to 0, which is an NGT, Q1 will also toggle, and it will toggle to become 0. I think I was correct in the first place. And this is also an active clock transition, and so that will also toggle Q2, sorry, because Q2 will toggle if Q1 moves from a 1 to a 0. So we should have a 1 here. We can continue and see how this goes. So this will toggle again Okay, 0 to 1, but because it is 0 to 1, that's a PGT, so that will remain in its state. And because there is no active clock transition here, that will also remain in its state. 6, this will now toggle, okay? It will toggle again to 0. 1 to 0 is an NGT, okay, which will toggle Q1. So Q1 will move from 0 to 1, but Q2 will remain at 1 because 0 to 1 is not the active clock transition we are looking for. 7, we toggle again, which is 0 to 1. Because it is 0 to 1, that's a PGT, it cannot toggle Q1. So Q1 will remain at 1, and Q2 will also remain at 1 because 1 to 1 is not a transition to set off or to toggle Q2. And then 8, you have 1. Oh, sorry, we have a 0 here because it toggles again. 1 to 0 is an active clock transition. So it toggles this one. That one toggles to 0. And 1 to 0 is also once again an active clock transition. So it toggles Q2 as well to a 0. 9, so you can see we are back to where we started. That is 0, 0, 0. We are sort of back to where it started. We toggle again, 1. 0 to 1 is not a PGT, so we remain at 0, and obviously remain at 0. 10, we toggle again, 1 to 0 toggles Q1. So Q1 now changes to 1, but 0 to 1 is a PGT, so that will remain at 0, and so on. Okay, so that is our truth table. Any questions?
Yes, sir. Kindly repeat for me what causes Q1 and Q2 to remain high at 6 and 7.
So if you look at 6 here, the clock transition is from 1 to 0 for the clock transition. So there is a toggle. Okay, so the active clock transition happens. Now 1 and 0, 1 to 0 is an NGT. So an NGT in Q0 will cause a change at Q1. So that's why Q1 toggles to 1. And because we are moving for Q1, an active clock transition or a change of Q1 from 1 to 0 would cause a change at Q2. But at from 5 to 6, you can see that that is 0 to 1. So that's a PGT. It is not going to act like a clock. It's not the one that the clock will actually accept. And so that is why Q2 remains 1. At 7, we are moving from 0 to 1. 0 to 1 is a PGT of Q0, so it will not set off Q1. That's why Q1 remains a 1. Okay, so Q1 remains a 1 because Q0 is changing from 0 to a 1, which is not a PGT. And then obviously, if Q1 is not changing, Q2 will also not change. It is until this point. I think there is somebody making noise for us. Jonas, please. At 8, it's at 7 to 8 where the clock, the clock comes in, Q0 toggles again from 1 to 0, and that's an NGT because that is 1 to 0, positive to negative. And so if this is happening in Q0, it will toggle Q1. So Q1 will move from 1 to 0, but also you can see that this is another NGT. This is an NGT, that's an NGT. So again, this NGT at Q1 will also change Q2, as we have seen in this case. Katumba.
Sorry, good morning.
Good morning.
I just clarification on something small. So in short, the Q1, Q0, Q1, Q2 only change when we have a clock transition according to the given clock, whether it's an NGT or PGT.
Yes, we only change when the responsible state that is running the clock moves from in an NGT fashion from positive to negative.
Okay, my other question is where do we start from? Are you specifically supposed to start from Q0 going to Q2, or you can start from either side you want?
I can start from any side I want, but you see the clock is on the Q naught. So things tend to happen from the Q naught side. So a trigger at Q naught might cause a trigger at Q1, and a trigger at Q1 might cause a trigger at Q2, and then Q2 will cause a trigger at Q3, and so on. So I think you can start from this side, but you would have in your analysis, you would really have to start from the clock side, moving through the flip-flops. Okay, so I think in the truth table, it's probably best to start with Q naught, where the clock is. I want to actually repeat the truth table for there's somebody who asked about it, but I think a lot of people would actually benefit from it. So I'm going to repeat the truth table. If you have understood it, it's okay. If you haven't, this is your chance to do that. Because I think if we understand the truth table, this stuff becomes very easy. And if you don't, then it is really difficult for you. So let us just go through the truth table one more time, and then we can move on to the timing diagrams. Okay. So once again, initially it is 0, 0, 0. But by the way, if I had told you that assume that I was in state 101, it would be the same. You can start your clock your things from 101, and it would be okay. Okay. So anyway, but let's start in this state. 0, 0, 0. After the first clock pulse, what happens? When the clock pulse comes in, Q naught will actually toggle, because for it always toggles because it has the actual clock pulse that we are having in this table. But Q1 would toggle if Q naught was transitioning in NGT, and Q2 only toggles if Q1 is transitioning in NGT sense, because you can see in the diagram, Q naught runs Q1 and Q1 runs Q2. Now Q1 cannot toggle here because Q naught is from 0 to 1. That's a PGT. So that should stay in the same state, and that one would stay in the same state. After the first part, when the second pulse comes in, this would toggle again. Now, because Q naught is moving from 1 to 0, that's an NGT. And that NGT here, okay, would cause actually a change in Q1 because it toggles that flip-flop. So that flip-flop goes to 1. Now, for Q2, you are looking at the transitions in Q1. You can see here for Q2, transitions in Q1. And here the transition in Q1 is actually 0 to 1, which is a PGT. It will not toggle that flip-flop. After the third pulse, 0 changes back to 1. That's a PGT. It cannot toggle the Q1, so the Q1 remains a 1. And now a 1 and a 1, there is no transition there, so that stays in the same state. 4, the fourth pulse, that transition is again to 0. Now this is a 1 to a 0, which is an NGT, which will cause a transition in Q1. That transition is a 0 from 1 to 0. 1 to 0 is also an NGT, so it will cause a corresponding transition or a toggle in Q2. So now Q2 becomes a 1. The fifth pulse, you have a toggle again, but this toggle is PGT, so it cannot cause a toggle in Q1, so Q1 remains at 0. 0 to 0 is no transition, so Q2 also remains at 1. 6, a transition is back to 0 here, the toggle is back to 0. So 1 to 0 causes a transition or a toggle in Q1, so Q1 goes to 1. Now, the toggle in Q1 is actually an APGT. It's 0 to 1, so it will not cause any change in Q2, so that remains at 1. And then 7, this will toggle again. So 0 to 1 is a PGT, so that will remain at 1. And 1 to 1 is no transition, so we still have a 1 at Q2. 8, now we toggle here. And this transition of Q naught is now 1 to 0, which is an NGT. So it toggles Q1 to 0, and a 1 to a 0 in Q1, a transition of 1 to 0 in Q1 actually acts like an active clock transition for Q2, which now also toggles to 0. And I wanted to tell you that you can see that actually we have gone full circle and gone back there. 9, 0 to 1. is a PGT, so that will remain at 0 and that will remain at 0. 10, that's an NGT now, 1 to 0, that will toggle that one, and 0 to 1 is a PGT, that will stay the same, and so on. But really you can see that after this state, we actually sort of, this state is mapped to that one, and the next is mapped to that one, and the next one to that one. So in other words, once we have reached the final state, you can see we have 1, 1, 1. That is really the final state. That is the highest number you can have with 3 bits. We always circle back to that. So from 7, I could have said circle back to that, and every time I reach 7, I circle back to that, and I circle back to that, because all these, no matter how many I do, they will just be repetitions of 0 to 7. Okay, so I hope that that one is clear. So does that mean we have to critically follow whether the transition is NGT or PGT for all cases of Q? Yes, you have to. And if this flip-flop arrangement was using a positive going transition clock, then of course you are looking for PGT, not NGT. We are using NGT here because of the bubbles, but if there were no bubbles, we would actually be transitioning actively on the PGT. All right, but yes, yes, Vivian, you must do that. Otherwise, if you don't get the active clock transition, you cannot toggle. Now, Jethro?
Yes, excuse me, sir. Is it a coincidence that all the possible combinations of Q0, Q1, Q2 are there from 0 to 7? Like 0, 0, 0, 0, 0, 1, those things, like up to 1, 1, 1.
It's not a coincidence. It is what it's supposed to be. In fact, that is one of the basically that is counting, because if I give you 8 things, you are counting them from 0 to 7, isn't it? So it is 0, 1, 2, 3, 4, 5, 6, 7, and those are 8 unique things. So it is not a coincidence, because in fact this is the counting application of the flip-flops in action. This is really the counting operations. You have got to count in steps. Also, just for if you notice here, they are actually in order. If we were to rearrange this into Q2, Q1, Q0, you see it is 0, 0, 0, 0, 0, 1, 0, 1, 0, 0, 1, 1, 1, 0, 0, 1, 0, 1, 1, 1, 0, and 1, 1, 1. They are in order. So we are now able to count. And if your items are more than 8, then you'll go back to 0, 0, 0, 0, 0, 1, 0, 1, 0, and so on. And so you can count your things in bundles of 8. I can count 8, put them aside, count 8, put them aside, count 8, put them aside. But if you want to count unique things, if they are less than 8, you can use 3 flip-flops. If they are less than 4, you can use, if they are 4 or less, you can use 2 flip-flops. If they are more than 8, maybe 12, you need 4 flip-flops. If they are more than 16 or maybe 20, 25, you need 5 flip-flops, and so on and so forth. And all of them can be connected in this way, so that the clock runs the least significant one, and then the output of that runs the next one, and so on and so forth until you reach the end. And that way you will be able to get your counting action. Charles?
Excuse me, sir. Is it a principle that transitioning from Q1 to Q0 to Q0 is by NGT? And actually, let me repeat it. That Q1 transition only when it is an NGT, and then Q2 transition only when it is a PGT, or it depends on the factors given?
No, all of these will transition only when the clock is an NGT, because you see all of them have bubbles. So Q0, here you can see the clock here, it will only cause the Q0 to toggle on the NGT, okay? Now you see Q0 is the clock of Q1. That's why I drew this thing. You can see Q0 is the clock of Q1. Now this Q1 does not know that it is being ran by Q0. For it, it thinks it is a normal clock. But the way we know how clocks work, or how these clocked flip-flops work, is that this is only going to toggle only if there is an NGT coming into it, whether it's from the clock or it is from Q0. So Q0 changing from a 1 to a 0 is the only point at which you can toggle that flip-flop. And now Q1 is also the clock signal of Q2, as you can see here. Q2 does not need to know where its clock signal is coming from. It could be connected to that main clock, or it could be connected to any other input. But as long as there is a transition here from a 1 to a 0 going into this clock's input, there is going to be a toggle. And in this case, therefore, this transition from negative to positive, from 1 to 0 is only going to happen if it is happening in Q1, because it is Q1 that is connected to that clock. Okay, so all of them are transitioning on an NGT, but that clock signal is coming from different sources. For flip-flop F1, if I can call it FF1, they are using the normal clock. FF2, actually I should say FF0. FF1, its clock signal is coming from Q0. FF2, its clock signal is coming from Q1, and so on. And we can add more flip-flops here, as I've said. Before Semakula comes in, let me just answer a few questions in the chat. This is Buhari. Q0 toggles because J equals 1 and K is 1 on our diagram. Is there a possibility of having J equals 1 and K is or no, equals not? No, there is no possibility, because we've said that we only toggle when J equals 1 and K equals 1. So you need to remember the truth table, Buhari. We actually, for the S and R flip-flop, J equals S equals 1 and R equals 1 would be invalid, if you remember. But we say that the difference with the JK is that the JK actually toggles. And so if we have a J equals 1 and K equals 0, this is the setting state we would be setting. And so we cannot, you can have them, the truth table would look different, but then you would not be, you would probably set all these flip-flops and then stop there, because once you have set, what else are you doing? But for us to actually create a counting circuit that can also divide frequencies, we need to keep our J and K inputs in one state, so that every time there is a clock transition, we can get the right toggle. Okay, that is the only way this part of the application of flip-flops can actually work. If we want to count, if we want to divide frequencies, we need to keep J and K equal to 1. And then we arrange our circuit in this way, so that we only clock the first flip-flop. The output of that flip-flops will clock the second flip-flop. The output of the second flip-flop will clock the third flip-flop, and so on and so forth. Hisham, would the different inputs in the next flip-flops change the table? If you have different flip-flop inputs, you mean J and K, we wouldn't have the toggle. You see, we need the toggle function, and that toggle function is only realized if our inputs are kept at J and K. Now, another question could be, what if I actually used the same clock in all of these? Then we would create something that we have seen before, which is where we were running or clocking all flip-flops in one go. But for this type of application, this is just take it as it is, basically. Why are we using this is Docus? Why are we using NGT to determine the toggle? I don't know if Docus has been attending, but the reason why we are using NGT is because we can see here the clock is a negative going transition clock. It has a bubble. These bubbles mean NGT. If there were no bubbles, it would be PGT, and the truth table would be different. And in fact, we are just going to do it for you. Okay. Patricia, if we change it to PGT, would it still produce the counting action, or that is something else? It would, and we are going to do it. Let us just do it after this. Yes, okay, but in a reverse order, yes, Abraham, that's true. Abigaba, pardon on the variation between the number of flip-flops required in response to the number of iterations. Yeah, you know that basically the counting is 2 to the power 3, okay? Sorry, 2 to the power n. So if you have 2 flip-flops, you can count up to 4 items. If you have 3 flip-flops, remember n is the number of flip-flops, which is equal to the n number of bits. And we know that 1 flip-flop equals to 1 bit. So in this case, we have 2 to the power 3, which is 8. That's why we have 0, 1, 2, 3, 4, 5, up to 7. Okay, so if I have 8 flip-flops, I will count up to 7. If I have 6 flip-flops, 6 flip-flops, Okay, these are 3 flip-flops. Okay, it is 2 to power n, which is 64, but actually the last state is 63, so it is 2n. I remember teaching this. Okay, if I didn't, I will go through it again. Thank you. Okay, great. Now, Musa, did you have a question?
Yes, good morning, doctor.
Good morning.
I'm like, the way I see these things is like if the crop given, the crop pulse given is the same. As if now it's the normal counting that we have been doing. Now, like for this is like for PJT, it's the normal counting, and for the N, we are just starting from the most significant counting normally still.
I don't think I've got your question.
Really that, or like I've been counting, like if I'm to draw that two stable Q of Q not Q1, Q2. If I'm start counting, I will say 0, 0, 0, 0, 0, 1, then 0, 1, 0, 0, 1, 1, like that.
Yes.
And yeah, by the way, performing that PJT, I think it will give us that. Then for NGT, I'm seeing that we are starting with this, the most significant bit, which is 2 note. Like here we shall be counting 0, 0, 1 coming to right. Then you will read this like you will read it as this is 0, 0, 0, then 1, 0, 0 in normal, but just changing the hand.
Okay, okay, so continue and we see if I understand, because I think the idea behind this counting, I've not done PGT for this one, so maybe it is the opposite, as Abraham said, but that does not mean that we are not counting, because at the end of the day, when you're counting things, you're giving them unique states. I can count you and say you are the first person, you are the second, you are the third, you are the fourth. If I start from up and I say you are the 100th, you are the 99th, you are 98th, and so on, I'm still counting. The idea is that you're able to uniquely identify each item using a different code, and that's the whole concept of counting. But I've actually not done the PGT. It seems some of you have done it, and I would like Patricia and those of you who are a bit intrigued to also do it, and you see how the counting is done. But if it is completely opposite of this one, I just want to give the explanation ahead that yes, in normal terms, we start from 0 to 1, 2, 3, 4 in that order. But even if I was counting from 7, 6, 5, 4 towards 0, the idea of counting here is that each item can be uniquely coded, you know, in a way that differentiates it from any other. So that's the uniqueness, and that would still be, there wouldn't be any ambiguity with that. Okay, so let's continue. Now, this is actually what we have done. I put this in the slides, it's not in the book. And you can see that it is 000, 001 up to 111. When we reach 111, the next is like we are looping back to there. So that's why I was saying earlier that we can do and you can go and do the one for 4 flip-flops. We are looping back to 000, going up to 111, because 111 is the highest unique number or word, and then we go back to 0 and we keep rounding and looping and counting, so that you can sort of count bundles of 8. So that's why this part is not necessary. But just to remind you, if we have n bits, which is equal to n flip-flops really, because each flip-flop stores 1 bit, then we can count 2n unique items, and the counting range will be 0 to 2 to power n minus 1. So like in this case, if n is 3, in this case, we can count 2 to power 3 equals 8 items, and those are counted from 0 to 2 to power n 8 minus 1, which is 7. Because actually the counting range is 000 2, 1, 1, 1. And we know that's a 0, and that is a 7. I remember we talked about this. Okay, so the unique items will be 2 to the power n, but the maximum counting state will be where everything is 1, 1, 1, and that will be 2 to the power n minus 1 in decimal terms. All right, so let us draw the truth table for this, and I want to draw these arrows, not arrows really, but just so that we draw something that is very near to scale. All right. So here you can see that we have retained the clock signal, okay, because the clock signal that one is predictable. We know how it will look like. And we expect that after the 7 bits, we should be restarting. So the state here should ideally be equivalent to the state there. And 9 and 10 and 11 and so on. Okay, so we are going to assume that things, we can start with Q0 here. I think that's what they start with, and Q1 later and Q2 later. So Q1 was initially 0. Okay, so it is Q0 was initially 0, so we can have 0 here. After the first pulse, it toggled to 1. Okay, 1. After the second pulse, it toggled back to 0. So we can see that for it will keep toggling in this way. And so on. Now, Q1 was also initially 0, okay? But we said that it will remain Q1, it will remain a 0 even in this transition. In fact, if you don't want to waste time, because we know now that Q0 is the clock for Q1, so you can look for the NGT on Q0. The NGT on, you don't have to waste your time looking at the table and trying to avoid making mistakes. You just look for the NGT on Q1 because that is the position at which Q1 the NGT in Q0, because that's the position at which Q1 can change. So we have, you see, all the way to there. Only on the NGT of Q0 can we toggle Q1, and then you see. Now for Q2, we are going to toggle on its NGT, which is there and there, only 2 places. So we will remain 0 until that point. Then we will toggle to that point, and then we will continue until we find another toggle somewhere. Now, if we had Q3, if we were dealing with 4 bits here, we would toggle Q3 at that point, and so on and so forth. But let us assume that there is no, okay, not assume, there is actually really no 0, 3. So if we look at the states in these positions, in this position, that's a 0, and a 0. And so if we are writing Q2, Q1, Q0, we can say that this state is 0, 0, 0. This state will be here 0. That one is a 0, but now Q0 is a 1, 0, 1. Here it will be 0 here, 1 here, and a 0 again. And then here it will be a 0 and a 1 and a 1, 1, 1. Now here in this position after the 4th pulse, we would have a 1 and a 0 and a 0. Here we would have a 1 and a 0 and a 1. I think now you already get the thing. And then we would have another 1 and a 1 and a 0. And finally we would have a 1 and a 1 and a 1 in this case. Then we go back to 0, 0, 0, 0, 0, 1, 0, 1, 0, 0, 1, 1. Okay, so it looks like after this position, we basically loop back, which is something that we are already aware of. And so that is the counting application of flip-flops. Now, there is a device that is designed using flip-flops. It is designed like this, and it is called a counter. Okay, I don't know if you've encountered this in your labs, but this is essentially a counter. This is how it is designed. Later on in the course, we are going to see counters that are ICs. Okay, it's an integrated circuit. It's a black box, but inside the connections are done in this way. Now, what about frequency division? If we see this one, if we see the clock frequency, let's say that this is the clock is maybe 10 Hz. That is 10 Hz. Okay, and if it is 10 Hz, it means that the period, you know, we say that F is 1/T. So we can say that the period is 0.1. That is the one that gives us 10 Hz. Frequency is 1 over its of the period of the periodic signal. Now, if we look at this, if we look at FQ1, no, FQ0, if you compare FQ0 and FQ1, this, if we take this position and the next repetition of this position is there, okay? So we are saying that this is 0.1 of a second. If we look at the period for this case, we are starting from this point all the way to that point. So this is the period for Q0. So for Q0, if I can say TQ0 will be 0.2. It is twice of that one. So the clock, the frequency of Q0 will be 1 over 0.2, which is 5 Hz. You can see that actually the clock signal has a frequency of 10 Hz, and the Q0 is actually now a frequency of 5 Hz. And if you look at Q1, you can see that the frequency for Q1 is half of the frequency for Q2. For Q0, because if you take, for example, this position and that position, in this case for Q1, it will be this position all the way to that position, meaning that the period here is twice the period of Q0. In this case, it would be 0.4. So T for Q1 will be 0.4, and the frequency for Q1 will actually be 2.5 Hz. And for Q2, we are looking at this position all the way to that position. And this is, I don't know how many seconds these are, but these are 8 times. You can see that you need in fact, Q2 will be 0.8 seconds. I know that I'm going through this very fast, but it's quite easy. And then FQ2 will be 1 over 0.8, which is 1.25 Hz. Let me show you a diagram from the book that is a bit clearer, and so it is very easy to follow. But actually, we have already done all of this. So you can see that this signal is changing at half the rate of the clock signal, isn't it? So if the clock signal is 10 Hz, you can see that if we take this position, this point and that point, because after that they repeat, you can see that this signal in that same period, it will have changed twice, from here to here and from there to there. So that means that the frequency of the clock is twice the frequency of Q0, meaning that FQ0 is 5 megahertz. And if we look at Q1, it's even slower than Q0. And in fact, it is half. So let's take a position like this one, this one, to that one. If we are looking at Q1, we are looking at this and that one. Actually, in this period, this one has changed once. This one has changed twice. In other words, it has repeated itself twice. So that means it has a frequency that is twice as fast as Q0, as Q1. So FQ1 will be half of 5, which is 2.5 Hz, not megahertz. And FQ2 is 1.25 Hz. And FQ3 will be, 0.625 Hz and so on. We always keep dividing by 2. Let me see some questions. This is Musa. There is no also frequency for HQ0. Togos. Okay. If I want to count up to 1,000, does it mean we need 1,000 flip-flops? No. You only need 2 to power n that is greater or equal to 1,000. Okay. So in fact, the flip-flops here will be 10. You need 10 flip-flops. 10 flip-flops, 10 to power 2 to power 10 is 1024. So if you have 1,000, they can be counted using 10 flip-flops. If you have more than that, you need to add a flip-flop and so on. We did this in the first parts of the course. So to recap, we have seen how we can count using flip-flops, and we have also seen how we can divide our frequency using flip-flops. If I have my flip-flops like this, okay, and I'm going to put them in an IC, and I have a clock signal, and I have my F out here, or an output signal, I will know that F out is equal to 1 over 2 to power n F clock. In this case, n is 4. So it will be, if F clock, no, F at the output will be equal to F clock over 16, since in this case I have 4 flip-flops. Okay, any questions? Okay, if there are no questions, any questions? No, Jordan, yeah.
Just a repetition on how you find F out.
S out. What is S out?
Sorry, F clock.
F out. Okay.
F
so
out.
I know, you see that every time we have a flip-flop, it will divide the frequency by half. So like this, if this frequency is 10, the next one will be 5, the next one will be 2.5, the next one will be 1.25. Now, if I compare 10 and 1.25, I can see that that is 10 over 8. That's how I get 1.25. And so that's why I said that actually at the output, because usually you'll see the final output, you will not see these signals inside. That's why I said that actually F out, if we compare with this case, will be F in, which is the F of the clock, the actual clock, over 2 to power n. And 2 to power n, in this case, these are 3 flip-flops, so 2 to power n will be 2 to power 3, which is 8. And actually, this is a formula, so it doesn't change whether you have 100 flip-flops or 1 flip-flop.
Okay, yes, thank you.
So,
excuse me, sir.
yes.
Like, how do we, are we always given the frequency of the clock, or like,
Yes.
how do we give it?
Yes. I will tell you that the frequency of the clock. So let me give you an example. In fact, let me give you a simple question. If the input clock frequency is 20 megahertz, I have a 5-bit counter. Okay. What is the frequency of the output signal? So that is a question. You do it for me. It's not a quiz, but I want to see some text. You know, you can chat, and if somebody chats your answer, you don't have to chat the same. But if you have a unique answer, you can pop it in there and I have a look. So most of the questions will be actually quite similar to this. So Grace Viribawa is 4 megahertz, Kasaja Pascal 0.625, Mugume Mark. So I believe the guys of 0.625 are saying it's a megahertz. I've seen 625,000, which is also 0.625, which is a megahertz. So that's okay. Yes. Okay, so yeah, so that's correct, because a 5-bit counter has 5 flip-flops, and that is n is equal to 5. So if I have my input signal at 20 megahertz, after the first flip-flop, it will be 10, because each flip-flop divides it in half. After the second, it will be 5. After the third, it will be 2.5. After the fourth, it will be 1.25. After the fifth, it will be 0.625. All of these are megahertz. But I say that the simpler way is to say that the F output is equal to F clock divided by 2 to the power n, which is 20 over 2 to the power 5, 20 over 32, which is 0.625. Obviously, I prefer the calculation approach to the graphical approach. The graphical approach, I just made it up right now. Okay, thank you. Thank you very much. So, let me teach you something, by the way. Don't say something like 6 megahertz. Every time write 6 and leave a space. Every time you're writing the units of a number, don't attach them. Don't say 20 meters. No, these are things for high school. We say 20 meters. This I'm just teaching you, because I usually see people in 4th year making these mistakes. Even people of masters make this. I'm just teaching you because I saw somebody, I saw all of your answers. You seem to attach the megahertz to the number. Right. The counting operation, we have something called a state transition diagram, which shows the transition of the state. So we started at 0, 0, 0. Yes.
Sir, kindly I will request you, before you look at this one, you help us fill the truth table for the PGT, because I've tried it and it is confusing me, kindly.
You have. Okay, let us see. Okay. Since we are here to learn, and since we can do that, I don't have an issue. Okay, so okay. So let us do a PGT. Once again, we have Q2, we have Q1, and we have Q0, and this is a PGT, JK, JK. This clock is run by Q0, and Q1 is running that clock, JK. And we need our J to always be equal to K to always be equal to 1. And this is our output. So now here, for this one to change, we need a PGT of Q0. And for that one to change, we need a PGT of Q1. So if we say clock Q2, Q1, Q0, let's start it like that. 0, let's assume that they start at 0, 0, 0. For the first clock, Q0 will transition to 1. And when Q naught transitions to 1, Q1 will also transition to 1. And when Q1 transitions to 1, 0 to 1, Q2, Q naught, I think I was supposed to start here. 0 to 1 will cause a transition in Q1, which is 0 to 1. And also this transition from 0 to 1 will also cause another transition in Q2, which is 0 to 1. Our second clock pulse, this one will toggle. And when it toggles, this will remain a 1. And if this remains a 1, this will also remain a 1. On 3, this will toggle again. By the way, I was supposed to start with Q naught here. That's why we are having a problem. But just know that I'm starting this side. We are going to have another 1. And when I have a 1, a 0 to a 1, it will toggle this one. So I have a 0. Now that is a 1 to a 0. That's NGT. So this will remain a 1. 4, this will toggle again. 1 to 0 is a NGT. So that will remain there. And there's no transition here. That will remain a 1. 5. That will now toggle to a 1. 0 to 1 will toggle this one to a 1. And 0 to 1 will toggle that one to a 0. 6. This one will toggle to a 0. A 1 to a 0 is no PGT. So we remain at 1. 1 to 1, no transition. We remain at 0. 7. That is 7. Then we have a 1 here. 0 to a 1 is a PGT that will transition to NGT to PGT. That's a 1 to a 0. That is still a 0. Okay. And then 8, 0 to a 1, we have a 0. 1 to a 0 is NGT, so that remains a 0, and that remains a 0. So that's 0, 0, 0, 0, 0, 1, 0, 1, 0, 0, 1, 1, 1, 0, 0, 1, 0, 1, 1, 1, 0, and 1, 1, 1. So from this point, we basically go back to where we started. So you can see that, and Abraham actually called this. I hope he had probably done it. Let me remove someone. Ndajire, I'm not going to remove you because you usually attend, but please mute. You're lucky that I remembered your name.
I'm sorry, sir.
It's okay. So Abigaba had already seen that. The order is altered. I didn't give explanation here because I was taking it that everybody, because we had already seen this. Kasago? Kasaja Pasco, do you want to say something?
Yes, sir. Thank you, doctor. And now for the case of an NGT, if I change the arrangement of Q0, Q1, and okay, sorry, Q2, Q1, and then Q0, and I use the normal binary counting, I think it comes out exactly the way it has to be.
Yeah, I don't know. I don't know why you are fixating on this one. This, I've already said that this is okay. Even if we are starting at 1, 1 and ending up at 0, 0, we are just altering the order, but it is still counting. And so in that context, I don't quite get what your worry is, but we have shown that in both cases, it works. And that is, in this case, we are looking at Q2, Q1, Q0. I am a bit against saying Q0, Q1, Q2, because we don't start with LSB, okay? We never start with LSB when we are doing our words. And clearly this is an LSB. We usually put LSB, the clock should run the LSB flip-flop. So I am not going to advise you to write it in this way so that it can count normally, because now actually that is a very grave mistake. Okay. But anyway, don't worry about this. Now, for Vivian, I believe it was Vivian, what we are doing is we are looking for an NGT. If I'm at 0, 0, 0, and then I put a clock, I'm looking first at this one. This is where the actual clock is. 0 to 1 is a PGT. And because it is a PGT, if it changes from 0 to 1, it should cause a change. You know, it's a PGT. If Q naught is changing from 0 to 1, it should change this one. If this one changes from 0 to 1, it should change that one. And so that's why I'm saying that 0 to 1 is a PGT, so it should change that one. So that should also transition to 1. But this is also another PGT that should also change that one to 1. And if you follow through that using that context or using that concept, it should be very easy. Now, in this case, it is 1 to 0. So it shouldn't change anything because 1 to 0 is an NGT. But 0 to 1 is a PGT. That's why it changes that one, 1 to 0. But 1 to 0 here cannot change that one because it is an NGT, and so on and so forth. Okay. So we start with LSB. No, we start with MSB. So when we are doing our counting, we should always start with MSB. This is standard, that your MSB is always on the left side. Okay. So we have reached 11:23. Why am I tired? I feel tired. I don't know why I feel tired. Okay. Let us Dion start with Q2, Q1, Q naught. If that is what, that is if you are counting. But when you are feeding the truth table, you should start with Q naught because that is where the clock is. So basically, our truth table here should have been, if you like, we should have had Q naught, Q1, Q2. But when we are counting in this manner. Although here we have seen that even when I was filling this table, I was starting with this one, then that one, then that one. If you want to do it in the way you are used to, you can do Q naught, Q1, Q2. But remember, when you're counting, you need to count as Q2, Q1, Q naught. Ivan, in the table, perhaps it shouldn't be either way. We've seen that it works, as in, you know, whichever. But when you're counting, always start with an MSB. Even for NGT, I think we are confusing each other here. What I'm saying is that when you're reading a number, what you have written in the truth table is not important because you can say clock, then here you say Q naught, Q1, Q2. You can also have clock, here you say Q2, Q1, Q naught. It doesn't matter. I'm just saying that if this is like, for instance, 0, 1, 1, this will be 1, 1, 0. But if I'm reading, if I'm telling you, I have to read it in terms of Q2, Q1, Q naught, because this is the MSB and this is the LSB. So maybe let's say that, I don't know what we can do. We can maybe take this approach when we are dealing with counters. I don't know. Either way, you won't be wrong if you are doing the right thing. The right thing cannot be wrong. So let us finish counters and then we move to, or can I have a short break? Let me have a short break and take a cup of water. Let's start at 11:30, just 4 minutes. You can have some water too.
I know to a break. Let me have a short break of 5 minutes. I take a cup of water.
Hello, I'm back, and I think, yeah, it is time 11:30. In the chat, Kaumdo Gerard is saying like him. I don't know who is talking about, but if it's me, how lucky am I? I'm not lucky at all. Okay, so so this is what we've done actually. This is the truth table. Okay, and you can see they've started with Q2, Q1, Q0. It doesn't really matter. But what matters are these counting states. So this is the state transition diagram. We start here, go through them 001, 01, 001. So you just draw the states, put them in circles, and draw arrows. And each arrow means a clock pulse. The original clock, the actual clock pulse. Okay, that's what it means. So after the first clock pulse, we move to that state. After the second, we move to that state. After the third, we move to that, and so on and so forth. Now, for those of you who were confused by the other thing, you could see that we can actually move from this state to that one in the same in a different direction, and it wouldn't change anything. At the end of the day, we have 8 unique states that can count up to 8 unique items. So this is a state transition diagram. And usually when I ask these things, I might ask you to draw the counter, draw the timing diagram, draw the state transition diagram. And I might also ask you a bit about frequency division. And all this might go for about 20. Very easy marks. Actually, this question, I like it. So I don't want to tell you that I will bring it, but I would, if I were you, I would make sure that I know how to do it. So there's something called the mod number, modulo. The mod number is actually it is simply the unique states of counting states. So in this case, our counter is mod 8. In fact, in reality, it is mod 2 to power n. So because our n was 3, the mod number is 8. So if I ask for the mod number, you see those are the unique counting states, which are 8 or 2 to power n in whatever case number of flip-flops. So we can say this is a mod 8 counter. We can have a mod 4 counter, we can have a mod 16 counter, mod 32 counter, mod 64 counter, mod 128 counter, mod 256 counter, and so on and so forth. Now, we can actually have a mod that does not follow a power of n, okay? So we can have a mod 6 counter, but this one we construct this in third year. If I want to count 20 things, why do I need to use a mod 32 counter? It will have some empty states that we do not need. So we can actually create a mod 20 counter. It is really nice to see how you can do this, and I can't wait to teach you how to do that in future. I don't think it can be done this semester, but in future it can in third year. And but for now, we just need to know that mod is a power of n for now. A fourth flip-flop would create mod 16, so all this is really easy. And so therefore, it can be that the output frequency is equal to the input frequency of the clock over the mod number. Okay, so like in this case, if mod number is 8, if our input frequency is the output frequency will be, if it was 10 over 8, that's what we were, this mod number, that's where we were having 1.25 hertz. So all very easy, and you can see how everything relates to each other. Any questions on mod? Okay, let us
Yes,
do a few.
just more explanation about that. I've not gotten anything.
You haven't got anything where? On the state transition diagram, on the mode number?
On the mode number, exactly.
But the mode number is very easy. It is not nothing new. It's something that we have already done. Let me just create a duplicate and try to explain afresh. Okay. So in fact, let me also remove that state transition diagram. Now we were saying that the mode number refers to the number of unique counting states. So if I have 3 flip-flops, I know that I can count up to 8. Up to 3 equals 8 states. So the mode number for a 3-bit flip-flop, sorry, a 3-bit counter is a mode 8 counter. If in this question here, I told you I have a 5-bit counter, I could have said I have a mode 32 counter, not a 5-bit counter. And then you shouldn't come and ask me how many flip-flops or how many bits are in a mode 32 counter. Okay, so the mode number is equivalent to the to 2 to power the number of flip-flops, so the number of bits that counter uses. Now, if I have 4 flip-flops, then the mode number is now 2 to power 4, which is 16. 5 flip-flops, 32. 6 flip-flops, 64, and so on and so forth. Now, a mode 8 counter counts from 000, because I already know a mode 8 counter is a 3-bit counter, to 111. So it counts from 0 to 7, but in this case 7 is actually 2 to power n minus 1. This is what we were saying earlier, that the actual maximum state is 2 to power n minus 1, but there is a 0 that you begin at. So when you add up everything, it reaches up to 2 to power n unique states. So if I have a mode 6 like this one, it will count from 0000000 to 111, 111. This is actually 63, and that is 0 in decimal. But we know that they altogether these states will add up to 2 to power n, which is 64 unique bits, unique states. Now we can also use the mode number to know the division. So if frequency division. So if I have a mode 2 to power n counter, it will divide my frequency in, my frequency out, the output frequency will be frequency in over the mode number. So it F out will be, in this case, will be F in over, like in this case, over 64. If it was a 3-bit counter or a mode 8 counter, it would be F out equal to F in over 8. And that's where I gave you an example of where we were using 10 over 8 and getting 1.25 hertz. So I hope that that is very clear. There's nothing much to speak about the mode number. That's pretty that about.
Okay, thank you, sir.
All right. So let us do some examples. Assume that this mode 8 counter, so we've already seen this counter, don't now start looking at the diagram. It's not any different from what we've seen. Assume that this mode 8 counter is in the 101 state. What will be the state after 13 pulses have been applied? Now, something that I may not have, that I can maybe use this one to, let's say we are in this state, okay? And this is a mode 8 counter. Mode 8. If we go through 8 pulses, we are going to be back to that state. If we go through another 8 pulses, we are going to be back in that state. So if you apply the number of pulses equivalent to the mode number, you will be back in the same state. Because you remember our truth tables here, we were saying, you know, how you go back or how you loop back and keep going through those loops. So it is essentially the same thing here. So if you are given a question like this one, first of all, you need to look at the mode and look at the 13 pulses. So in this case, if it were me, I would say, okay, mode 8 counter. I'm currently in state 101. After 8 pulses, I'll be in 101 again. After 9, after 10, 11, 12, 13. Okay. After 9 is 110 because I know how I'm counting. 111, 000, 001, 010. So after 13 pulses, I will be in that state. Now, somebody could have said, okay, I'm in 101 state in the, what about after the first pulse? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, all the way to 13. And then you say, okay, 110, 111, and so on. You will find actually here that you are still in 0, 1, 0. So my point is that when you get a question like this, don't be scared by the large number of pulses. Just see, take out the pulses that are equivalent to the mode number, and then you will end up with a few pulses to add. So for instance, let me say that I have a mode 8 counter that is in state 10. What's happening? 100. Okay, that is my state, 100. What state am I in? Am I in after 65 pulses, for instance? Oh, so now you look at this, you're like, do I have to do all 65 pulses? In fact, you don't. You are in state 101. After 8 pulses, you'll be back here. After 16, you'll be back here. After 24, you'll be back here. In other words, every time you do 8 pulses, which is equivalent to the mode number, you come back to the same state. After 32, you're back here. After 40, you're back here. After 48, you're back there. After 56, you're back there. After 64, you're back there. Okay. So now at 64, I know that I'm in 100. So that means after 65, I'll be in 101. Okay, very easy. Otherwise, you wouldn't have to do all these pulses. I can even give you, what about 1,000? You just keep jumping until you reach what you're looking for. Any questions on this?
Yes, sir.
Okay, you can ask.
Does it mean, like on the counting of the yes, sir. So does it mean we count, as in said, we count on the modes, like for instance of the 8 until we first cover the number of pulses, then you add 1 bit.
Then you add the next, yeah. So if your mode 8 has a 64 in it, then if they had said 65, you add 1 pulse. If they had said 67, you add the 65th, 66th, and 67th. If they had gone to 74, we would add an 8 and first get to 72, and then do 73 and 74. Okay. Okay, is that okay? Baganzi.
Good afternoon, doctor. I am kindly asking that you please repeat for me. I didn't understand.
Everything?
No, not everything. From the mode 8 counter, state 100, there was something you're explaining that number there, but I didn't understand.
That number is a state. So basically, what this question is saying is that you do not always have to start in the 000 state. You can start in any state. Okay, but when we were doing it earlier, we saw that every time I see a few other people have raised their hands. When we were doing it before, we were saying that actually, if I'm in this state, if I apply pulses, let's say I'm in this state, whatever state that is. If I apply pulses that are equivalent to the mode number, I will come back to that state. I will have gone through all these other states and I'll be back to that state. If I apply the same number of pulses, I'll be back to the same state, and so on and so forth. And so in this case, if I'm in state 101, if I apply 8 pulses, which is equivalent to the mode number, I will be back in state 101. Now, if I apply another 8 pulses, it takes me beyond what they have given me as 13. If I applied 8 pulses, it would take me to 101. But after this point, you can do 9, 10, 11, 12, 13. Okay, that's where we stop. But if we had said, what is the state after 35 pulses? There are people making noise for us. Please make sure that it's not you. After 32 pulses, we could have, say, we are in state 101. After 8 pulses, we are back there. After another 8, which takes us to 16, we are back there. After another 8, which takes us to 24, we are back there. After another 8, which takes us to 32, we are back in that state. So at 32 pulses, my state will be still 101. Now, they have given me 35. So 33, 34, 35. Now I can do normal counting, which is 110. This is 111. And then that means after 32 pulses, I'll be in the state 000. So you need to use the state you've been given, the current state, and the pulses you've been given, and the mode number to reduce the number of pulses or counting that you have to go through to get the actual answer. Kasaja?
Thank you, Doctor. Now, following the state transition diagram, if I want to find which state will my counter, okay, which state it will find after anything movement, so maybe like 13. If I try to follow it in, is it clockwise direction?
Yes.
It will give me exactly what an NGT will do. Following the other criteria you have used, if it is a PGT,
the one of going backwards.
Yes, the one you have followed. Will it give me the same thing for a PGT, or they do specify? Because if I follow a PGT, then I'll have to move anti-clockwise for me to get
anti-clockwise. I think in general you'll find that these counters are negative triggered, negative transition triggered, negative edge triggered. But if I specify, then you have got to do it the opposite way. But I don't think that is going to come up.
All right.
So yeah. So if we are in state 101, which is this state, we are saying that this is the current state. After 8 pulses, we are back into this state. Then you can say that the 9th is here, the 10th is here, the 11th is here, is the 12th is here, is the 13th is there. That is how we ended up in 1010, same as whatever, the thing I hid here. Okay. I think everyone is happy now. Okay. Wonderful. Charles?
Now, sir, if you're given a counter which will remove in so many states, like the previous example you have given, the one displayed on the screen, do we, am I supposed to say like after 80, it will give me it will be state 100. Then after 16, it will be still equivalent to 100 until when I reach that state where I should add, or because, I have to use these other routes you've done.
No, you can, I don't know how you can do it very well, but if I have, say I want you to tell me after 130 states, right? And I know that 128 states are within mod 8, you know, so like 128. I will say that I can just simply start, if I'm writing my answer, I say after 128 parses, state is 101. And then I say 129, 130. And so I'm not really looking for all this explanation. I just use this stuff so that you guys can understand better. I also don't usually use the state transition diagrams. I expect something very simple like this. But usually for an answer like this, I'm actually looking for the final answer, right? It's probably 1 mark or 2 marks. So I'm looking for the final answer. If you have it, you get the mark. If you don't have it, you fail. I'm not looking so much for the working, really. Yes, Ivan, he talked about it, I think Kasaja, and I said that it's probably going to be the case that we are using NGTs only. We don't usually use PGTs for counters, which is why you'll not find it in the book. But if it is a PGT for some reason, I'm running crazy and I bring it, you need to go through the right direction. So if you move in the right direction, the answer might be different, and it probably should be different because obviously we are using a different clock transition, active clock transition. Right, let's do an example, and I think this one will take. This is an example, it's not a quiz. Today, I don't want to give you a quiz. Somebody said that you are tired of me. I don't know why. If you're the one who is tired of me, you know, I'm trying to help you. Okay, so let us look at this example. We consider a counter circuit, but I thought you enjoy quizzes. It's fun, it's fun. This contains 6 flip-flops wired in the arrangement of a counter. So part A, what is the mode of the mode number? Let's start with part A. What is the mode number? Please give me the answer in the chat. If somebody puts your number, don't text it, since you know I already know it. Okay, so it is 64, which is 2 to power 6. Okay, 6 flip-flops. Okay, thank you. 2, determine the frequency at the output of the last flip-flop when the input clock frequency is 1 megahertz. Can you put that in Haz for, okay. It is, okay. Which is 0.01565 megahertz, which is 15.625 kilohertz. Okay. Yeah. Okay. You should, when you write hertz, make sure that the H is capital, because and part C, what is the counting states of this? What is the range of counting states for this counter? Okay, I would rather, that is good. I would rather that you write them as 0, 0, 0, 0, 0, 0 to 1, 1, 1, 1, 1, 1. Okay, so when we say counting states, let's write them using the bits in base 2. Okay, thank you. And we assume a starting state of 0, 0, 0. What will be the counter's state after 129 parses? Okay, part B. Okay, a lot of you have 0, 0, 0, 0, 0, 1. And this is because 64 times 2 is 128. Okay, so after 128 pulses, you're still at 000,000, and you at the 129th pulse, you count once, 0001. Okay, now what if I modify this and I say that I was at in state 01, 001, 1, and then I'm doing 132 pulses. What is my state after that? This is my current state. I start at this state and I apply 132 pulses. What is my new state? Okay, Jethro Chigobe has 01, 0, 110. Okay, let us see. So after 128 pulses, I will have 010, 011, 129, 130, 131, 132. Now this is where you need to know how to count. So I have 010, 100, 010, 101. This one is 010, 110. This one is 010, 111. Have I made a mistake? Because I see Jethro's is different. 100, 101, 110. Okay, so I think I may be the correct one. Okay, yeah. So most people have the same as me. Yeah, Shakira, Charles. Report, you have a different one. Ivan has the right one. Nava, you have a different one. Nagawa has the one similar to mine. Okay, so I think when you write it in this way, okay, I like to write it in this way because I think that when you write it in this way, you really cannot make a mistake. Okay, same picture also has the same as me. So let us move on. I think I might have also these exercises. So, number 1, what is the answer? A 20 kilohertz clock signal is applied to a JK flip-flop with J equal to K equal to 1. What is the frequency of the output waveform? Yeah. It will be 10 kilohertz. Thank you. And the reason is because if we have one flip-flop, if the clock is 20, it halves it by half. So okay, it doesn't, you know, it halves it by half is poor English. It halves it, so this will be 10. Number 2, how many flip-flops are required for a count of 255? Nagawa, Nava, yeah, that's correct. That's correct, Nava. 8 flip-flops. It is basically 2 to power 8, which is 256, but the counting stops from 0, starts at 0 and ends at 255. And then question this one, mod what? Yeah, mod 256, very good. I feel like today you have learned. What is the frequency of the output of the 8th flip-flop when the input clock frequency is 512 kilohertz? Number 4. When I was at campus, I used to live in Mitchell Hall. And if in our time, we didn't have money to go to the canteen. So if the lecturer got towards midday, I started getting uncomfortable. But you guys are different. So this will be 512 times 1 over 2 to the power 8. And 2 to the power 8 is what? Is 256, as we've already seen. So we are looking at 2 kilohertz, brilliant. And 5, finally, but now if you start here, okay, let's start there. And we are looking for 520. Actually, we know that 2 to the power 9 is 512, okay? So at 512, you have 0, 0, 0, 0, 0, 0, 0, 0. So you're looking for states up to 520 parses. And that should be quite easy for you to do. In fact, everything is happening around these 4 bits. The rest will be 0, 0, 0, 0. So it's, yeah. So next week, not next week, on Wednesday, we are going to start with this one. We have a few things to go through, but we are going to start with this one. And this is a microcomputer application that requires a bit of time for me to explain what is happening. Yeah, so if you're going from 512 to 520, if I added 7, I would get, that means 519, I should be at 0, 0, 0, 0, 0, 1, 1, 1, meaning at 520, I'm at 0, 0, 0, 0, 1, 0, 0, 0. Okay, so that is really good. That is John, yeah, John Trevor, that's really good. Right, come to the end of our lecture. I think that if you do not give me any conclusive feedback, we will do our test on Saturday. By the way, your class representatives can also fix the test. They can come and say, oh, let's do Saturday if it's convenient. That's, you know, they are class reps, they do work, so that's their part. Those are their perks. They can do things that are convenient for them. So I want to encourage Jesse and Mark, and I think Martha, and somebody else, Joan or somebody, that you go with a timetable that is convenient for you guys, because we may not have a scenario where everybody agrees with you. Okay, you are here to make decisions for everyone. Have a nice day, have a nice whatever, and we will meet again on Wednesday. See you then.